Okay, good morning. I just finished another presentation. We just talked about 萌芽计划. That's a very relatively large industrial university research project. Okay, today we will continue our discussion about chapter 1. The most important part of chapter 1 is, if you remember, is the Green theorem. But before we start, I would like to show you this one. This is the lecture notes. Hard copy. If you like, you can go to TA's office, room 119, and take a copy. Okay, room 119, the first floor, our lab, to take a copy for free. Okay, for free. Lecture note for free. And also, the electronic version is also uploaded. So if you don't need a hard copy, you can use your iPad or your notebook to study the material by yourself. Okay. Today we will continue our discussion about Green theorem. But before we start, I would like to remind you what we have learned so far. So let's go back to the very beginning. Introduction, Green theorem. Green theorem is actually a simple application of the divergence theorem. Divergence theorem is shown here. Just a moment. This is the divergence theorem. And Green theorem is just a simple application of the divergence theorem by substituting this vector to here and here. And we got these two. That's the Green first identity. And then interchange phi and the psi. So we got another equation by substituting these two equations, a dot b, b dot a. So cancel the same. So this one minus this one minus this one. So we have volume integration and surface integration. So the major advantage of the Green theorem is it's a combination of volume integration and surface integration. That gives us a lot of freedom, much easier to deal with. Okay, Green theorem relates a volume integral. This is the volume integral, T given to a surface integral. And this volume and this surface are closely related because the surface must be enclose the volume. So, and we will deal with Laplacian operator, Laplacian. These features are useful for the manipulation of the Poisson's equation. This is the Poisson's equation, can be, or Laplace equation. Remember, when we study electromagnetism, we study Poisson's equation, Laplace equation, specify the boundary condition and solve the Laplace equation. But now we are going to solve Poisson's equation, much more difficult to deal with. We are going to solve Poisson's equation with finite boundary, not infinite space, finite space. So we are going to deal with much more difficult problem. Actually, the problem is simple, but the solution is quite difficult. Okay, how to apply the Green's second identity? I will show you, but here, just show you, in order to use the Green's theorem, we need to introduce a delta function. This is the Dirac delta function. Dirac delta function. Very useful and very important. We are going to use the Dirac delta function to help us solve the solution. So by substituting this one and Poisson's equation substitute to here, and eventually we got this one. That's a simple application. I will talk about this topic over and over again. And we will find the Green function. This is the simplest Green function, 1 over R, or this one. This one, okay? So we already familiar with this one, with infinite space. But now, if the space is not infinite, we should consider contribution from the surface. And here we have some strange notation. And be careful, here, equation 1.35, we use the X unprime system. But here we change to the prime system. Be careful. The physics meaning is slightly different. We change the variable only for our convenience, for better understanding. So if the space is infinite, 无限大, infinite, then it will become the simplest case. V is all the space, all the space. It's good for simple case, but not very realistic for your laboratory. So for your study. So therefore, it's not simple. And 1 over R is the simplest Green function. Okay, 1 over R, that is this one, is the simplest Green function. And then we talk about delta function. We consider delta function as the basis for all the students. You should learn before. But I know you are not, I know you must learn the delta function, Dirac delta function. But I just give you another chance to familiar with Dirac delta function again. So that's very useful. You will use Dirac delta function frequently. So you should study this part. And Dirac delta function can be expressed in Cartesian coordinate SYZ or S1, S2, S3, or cylindrical coordinate rho phi z. This also pronounced as rho phi. So we have 3 expressions for phi, 3 notation for phi. And rho is the from here to here. But sometimes this rho will be confused with charge density. So we should be careful about the notation. Okay. In terms of spherical coordinates, that's another one. Okay. And we don't really care about the detailed structure of the delta function. It can be expressed in this form, this form, this form, doesn't matter. The delta function can be represented analytically by the following function. Okay. The integral must, the delta function must be, the delta function will have meaning if we perform the integral. Okay. And I also give you 2 examples. These 2 examples are very useful, simple example, and could be reappear in your quiz or other test. For example, this is a ring. Maybe we have a straight wire, and we have anything you want, any unique spherical shell, okay, something like that. And this is how to prove. This one is related to this one. A simple proof, separate into two parts. Okay, so today we will give you another applications of the green function, green theorem. That is the uniqueness of solution with Dirichlet or Neumann boundary conditions. We will give you two boundary conditions. One, Dirichlet boundary condition, which means the potential is specified on the surface of the boundary. Potential, surface. The subscript S means the surface that is specified or given. Another one is Neumann or Neumann boundary conditions. That is the normal component, of the change of potential. This implies the potential, and this is actually related to electric field. Okay, electric field. The normal component perpendicular to electric field. And so this one is specify the potential. This one is specify the electric field. Okay, you can specify the potential or electric field either way, but obviously potential are much easier to deal with. Because if you want to specify the potential on a conductor, just connect to a constant potential, then you can specify. Okay, so specify the potential is much more convenient for us. Therefore, Dirichlet boundary condition is much more easier to deal with, and much more realistic. Therefore, we prefer Dirichlet boundary conditions for this reason. As another application of the green theorem, we use it to prove the uniqueness theorem. Unique 唯一的 uniqueness theorem 表示 the solution is one and only one. So the Poisson's equation, for a given Poisson's equation and given boundary condition, this one or this one, the solution will be unique. Only one solution. Let me show you. Let me prove to you. Let's take the Dirichlet boundary conditions as an example. This is the volume. And we have a charge distribution inside. And this is the surface. Okay? And in a normal direction, from inside out. Remember, the boundary normal direction is from the inside out, pointing outward. Okay? And this is the Poisson's equation. Rho should be charge distribution, depends on position. And phi is the potential on S. Surface enclosed this volume. This is the Dirichlet boundary conditions. Okay, if some student, for example,王晨，你是真的叫王晨吗？还是王一晨？
没有，我是王晨。
哦 ，OK， 因为我们实验室有一位学生叫王一晨，他的成绩是班上第1名的。
他是学长，我知道他。
你认识他？
没有，就知道他而已。
好的，好，你应该认识的，认识王一晨。好，王一晨，假设 you found a solution phi 1 satisfy Poisson's equation, and phi 1 also satisfy the boundary conditions. And let's have another one. For example, 江俊彦, he found another solution. Phi 2 also satisfy Poisson's equation and satisfy the boundary conditions. Okay. Wang Chen got phi 1. Jiang got phi 2. Which one is correct? That's the problem. Okay, so we can define a vector called u, and that's definition phi 1 minus phi 2. So we can change these two equations into Laplace equation. And therefore, u on the surface will be 0 on surface. Okay, we change from Poisson's equation to Laplace equation. Laplace equation, no, source free. And then substitute to Green's first identity. Green's first identity. Phi per psi, O equals to U. And so you got this one. And substitute phi per psi, U. And we already know U will be 0 because it's Laplace equation. And this one, because of the surface, is 0. Therefore, this term is 0. This term is 0 as well. Therefore, divergence U dot divergence U, that is the absolute value of, gradient U squared, absolute value will be 0. So the only solution will be gradient U equals 0 everywhere within the volume. Gradient U equals 0, which means U is a constant only. 0 or a constant. And which means Wang Chen 跟江俊彦 their solution just differ 0 or a constant. Okay? They differ by at most a constant. At most a constant. So we don't care about the absolute value of the potential. We care the potential difference. Potential difference makes sense. Absolute value of the potential, we don't really care. Keep this in mind. Okay, so we prove all the solutions should be the same. So we got one unique solution. Therefore, we don't care about how you solve the problem, provided that you satisfy Green's theorem, Poisson's equation, and you satisfy the boundary condition. Then we got the correct solution. Okay. Therefore, to give you a lot of freedom, you can solve you can use different techniques to solve the solution, provided that the solution is satisfy the Poisson's equation, satisfy the boundary condition. Okay, that's the only requirement. Okay, let me show you another. Let me show you the green function. We just show you the simplest green function, 1 over the absolute value s minus s prime. Okay, that's the simplest green function. Now, I want to give you the general solution, the formal solution of electrostatic boundary value problems. That's the green function. Not always that simple. Not always. Don't worry. Complicated green function, use this. So we just need a simple green function only. So I will give you a simple green function, but the green function will be expressed in various forms from electrostatic, magnetostatic, electromagnetics. Okay, so we will use green function throughout Jackson. Therefore, green function is the backbone of electrodynamics. You should learn green function thoroughly. You should be familiar with the green function, the idea of green function. Okay. Green function allows us to solve all the problems, provided that you got the green function. The next step is just perform the integration. Okay, very simple. Find the green function first. Use the idea of symmetry. And then use the green function to solve all the problem. Simple. But green function looks like a huge knife, 牛刀. Not always convenient because 有时候用美工刀就可以了，小刀就可以了。Okay, as a powerful tool. Okay, so we introduce the green function GD. GD is Dirichlet boundary conditions. Okay, D, the subscript D means the Dirichlet boundary conditions. We have two variables, X and X prime. X and X prime, two variables. In electrostatics, the green function is the solution of the following problem. Okay, the green function is Dirac delta function, point source, and on the surface it's 0. It's 0 on the surface. We prefer Dirichlet boundary condition, so we use D here. Okay, that's another requirement. Another requirement. So X is the variable of the differential equation. X is the variable, and X prime is treated as another variable, not a constant. But since we have two variables, X, X prime, under this case, this one is unprime, so it will only operate on unprime. Okay, that's why. And X is the variable. So you can consider S prime as the source, X as the observer. Source, observer. And you can change the source to another source, to another source, to another source. And also you can change the position of the observer. Observer can be here, can be here, can be everywhere. Okay, so normally, X means observer. Observer is a variable. S prime means source point. Source point. And if you have multiple sources, a lot of sources, then you can perform the integration by consider all the contribution of the source. Okay? Okay. And you can also consider these two as a variable, different viewpoint. Okay. So maybe help us, the green function help you to familiar with the integration with calculus. Symmetry property, GD, what's the difference between these two? And consider two equations. The first equation is this one. Second equation is this one. What's the difference? We consider S as source, S prime as source, and Y as the variable, Y as a variable. On the surface is 0. What will happen? Substitute to Green's second identity. Phi as this one, psi as this one. Substitute to here. And eventually we got this one, Dirac delta function again. And this one is 0 because we specify it to be 0. This one is also 0, given. Okay, so interestingly, the left hand side, that's the only equation we got. Only when Y equals S prime, we have value. Only when Y equals X, we have value. Therefore, eventually we got this one. GD X prime X minus GD X prime. Okay, we got this one. We got this one, which means green function is symmetric. Symmetric. Okay, green function is symmetric. That gives us very convenient because the green function is symmetric. We like this property very much. So you can use this property to test the correctness of your green function. For example, sorry, very difficult for me to draw this one. Ugly. Yes, ugly. Let me try. Let me use another notepad. Where is my mouse? Or here. Obviously, that's symmetric. That means you change S to S prime, you all S prime to X, the solution should be the same. Yes, symmetric. So you can check the correctness of your green function using the symmetric properties. Okay, next one. So let me show you the formal solution. The formal solution of electrostatic boundary value problems. We will use this formal solution. Okay, first, we will consider a general electrostatic problem, boundary value problems. That is just like this case. Let me change. We have a surface and we have source inside this surface, and we have potential specified on the surface. So we consider Poisson's equation. That's the Poisson's equation, okay? And on the surface is specified or given on the surface. That's the general problem. And we will use the green second identity. Here, we change to prime. Everything is prime system. Okay, be careful about prime and unprime. Okay, in equation 1.35, this equation is related to Jackson. This equation is our equation only in the lecture chapter 1. Okay, so this equation is related to Jackson third edition. Okay, in 1.35, we let be the solution of variable. We just replace this one with this one. That is, you can change the variable prime, okay, and substitute this one to here. Then psi to be the Dirichlet green function, GD, Dirichlet green function. And this Dirichlet green function satisfies the Dirac delta function. And on the surface, it's 0. That's given. Okay. We hope to simplify this one because here we have 4 terms. 1, 2, 3, 4. Too much. And if we specify this boundary condition, this one will be 0. Cancel. So we reduce 4 terms to 3 terms. That's our purpose. With the green function, we can reduce from 4 terms to 3 terms only. 3 terms only. Okay. Can we further simplify the calculation? Yes. Yes, let me show you how to do that. This one substitute to here. This is integral Dirac delta function. So the solution will be only one value, x. Okay? The next one, substitute everything to here. Substitute everything to here. 0. This one, easy here. This one, minus, minus. So we got another one here. We have a minus sign. We have a minus sign here. It should be plus. And move to the right. Move to the right. We have another minus. Here is minus 4 pi. So change the symbol. Plus, plus. Okay? Okay. We saw this. We saw similar equation before. Similar equation before. Okay? But we still have one term left. That is this one. This one is 0. So we still have one term left. One term only. So we reduce 4 terms to 3 terms. And we have potential is shown here. It's not, you cannot perform the integration unless you know the distribution of the sign. So equation 1.44 expresses the solution phi of the general electrostatic problem in terms of the solution Green GD, Green's function of the point source problems and the boundary value problem phi x specified on the surface. To evaluate equation 1.44, we first solve GD, then substitute GD into this equation. So we need to find GD. What is the GD looks like? Okay. Actually, GD is satisfy the point source, and on the surface is 0. 2 requirements. Okay. Satisfy the point source. Satisfy the point source, and on the surface is 0. Of course, you can specify on the surface is not 0. Then you will consider these terms only. It's up to you. If you specify Dirichlet boundary conditions and on the surface is 0, then you can reduce 4 terms into 3 terms. If you don't do that, that's fine. If you have a lot of time and you don't want to do that, then you can use any function you want. That's still correct. Remember, Green's first identity and second identity always correct for scalar function phi and psi. Always correct. Okay, so it's up to you. But if you, for your convenience, you can specify the boundary of the Green function to be 0, then you can drop these terms. That's our purpose. So the solution will be very easy. Actually, not easy. Okay, but the Green function is the function to be find. If we find the Green function, yeah, we almost solve everything. That's good news. So find the Green function is the most important challenge for us. But don't worry, most of the case, the Green function will be easy. Unless you use, we will use all the techniques we learned before. We learn when we are sophomore students. Electromagnetism. Okay. Here is a case. Here is a case, but it's optional. So if we have a boundary here, hollow cube, 一个中空的 盒子 and has 6 square sides, and one side is fixed. The other 5 sides are grounded. Okay, what will happen? In this case, no charge. Okay, so all you need to do is consider the contribution on the surface. Before that, we don't know how to do, but now we can use the Green's theorem. We can use the Green's theorem. Now, consider we have a charge here, charge here. How to solve this problem? That will be almost impossible to solve this problem unless you can find the Green function. And the Green function for this rectangular box is not easy at all. Okay, not easy. For a sphere, yeah, it's easy. For a rectangular hollow cube, not easy. For a cylinder, not easy. For this one, you need an eigenvalue problem. We will learn in chapter 3. For a sphere or spherical shell, you need Legendre polynomial, spherical harmonics. For a cylinder, you need Bessel function. Okay. Okay. The idea of the Green function is easy. But in terms of different coordinates, Cartesian, cylindrical, spherical, you need a special function to represent. But the basic idea is quite simple. Okay, that's it. We will stop here. Okay, what time? What time is it? We just spent 40 minutes, less than 40 minutes. The rest of chapter 1 is homework. It's homework, but I want to show you something. Just a moment. I want to show you a slide.
是 OK 问问题吗？
Okay, you can ask any question you want.
Sir, I'm a bit confused. Why are we talking about the boundary condition for Green's function? Because the problem we want to solve is for potential. So shouldn't it be enough to specify the boundary condition for potential already? Then why are we talking about the boundary condition for the Green's function? Of course, it's nice we can kill one term, but I'm a bit confused why won't that be kind of over specification?
Actually, we don't over specify the boundary condition because we're given the boundary condition and we're given the potential distribution, and then we solve the potential inside.
Yeah,
Okay.
but we give both the boundary condition for potential and the Green's function.
We just give the boundary condition only, not the potential inside. Not the potential inside. Just boundary only.
Right.
On the surface of the volume only. So not over specify. For example, if we consider infinite space, then the space very, very, very far away, right? So in that case, we don't have to worry about the boundary because the boundary is very, very, very far away. Okay, so for undergraduate course, we always consider the simplest case, infinite space. Infinite space. So, and remember, we also try to solve a Legendre polynomial, spherical harmonics. Griffiths tried to solve these two equations. 现在是谈到零在问吗？
对。
好 ，maybe you can use Chinese if you still do not understand.
我在问的是为什么我们要考虑 Green's function 的边界条件 GD，因为我们不是在解，我们不是在解 potential phi 吗？那不是给 phi 的边界条件就够了吗？那为什么要给 GD 的边界条件？
为什么要给 GD 的边界条件？因为我们还需要另外一个 boundary condition 才能决定 D 啊 ，GD 啊。
那这样不会给过多吗？就是 GD 不是应该就是你的所有的电荷的分布就已经给定了吗？
没有啊，没有啊 ，GD 是 GD，你有两个function，一个 function 是假设哈 Green Theorem 里面有一个是 phi， 另外一个是 psi， 对不对？那你 phi 跟 psi 的 boundary condition 可以各自决定啊，
对，
各自决定，所以没有关系的。
那这样不是就已经可以保证唯一性了吗？那为什么还要考虑 GD 的边界条件？
你需要考虑 GD， 你还可以唯一把 GD 给决定下来 ，otherwise 你没有办法决定 GD 会是什么。
对，
对，所以 GD 必须要知道才能够决定。
嗯哼，
对，就好像是 potential 在 boundary 必须要知道才能够决定。
好，了解了，谢谢。
我现在要分享这个，为什么现在没办法分享？我先停止共用。Just a moment. I would like to show you another slide. Not slide, another. Okay. How do you like this photo? This mean. Can you see this photo? 嗨，洪俊，你们可以看到这幅吗？
可以看得到。
How do you like this one? When Newton wrote this equation, that's the gravitational force. And Coulomb, he just saw this equation. And he changed the notation from G to K, from M1 to Q, and separation from D to R. Very interesting. That means most of the physics law looks similar in some way. So I just show you how to solve the green function. And later on, we will use green function throughout the Jackson. The green function, don't worry, in most of the case, are very simple. So don't worry too much. Okay. Although I just told you green function will be very powerful. Once you know the green function, you know everything. Okay, just perform the integration, volume integration, and surface integration. That's it. However, green function can be expressed in different coordinates. Okay. So how to use the green function? Starting from diverging theorem. So chapter 1, we will talk about only a few pages only, not too much. Okay, I will stop here. Any question? Any questions so far? So it's not a surprise to find the Coulomb's law. Maybe I should give you more information. I quickly go through chapter 1, the rest of the chapter 1. Electric field, just a definition, force divided by unit charge. And test charge is very, very small. Okay, infinitesimal, 非常非常小. So we won't change the field contribution. Extremely small, infinitesimal. Okay, so the existence of this Q is do not change anything. Okay, in that case, we can calculate E. That's the definition of E. Let's define E. Okay, in the old time, we know we will perform this one. But how do we know? Because Coulomb law, gravitational force tells us that. Cavendish Laboratory, he used a test chart and test maps, and he can measure the gravitational force. And Coulomb used a similar idea. So he write a similar equation. Okay, not surprised. But now, with the green function, we have a more complete, more reasonable. We not only consider the contribution from the volume, but also consider the surface enclosed this volume. In that case, we don't have to consider infinite space. All we need to do is consider finite space. Finite space. 谁有那个精力去考虑无限大？你哪知道无限远的地方发生什么事情？你做实验的时候都是有限大，都是 finite 的。啊，所以这个 Green Theorem 才是一个漂亮、完整、好用的式子。无限大的地方，对啊，到底发生什么事情？不知道啊，也不需要知道。OK， Gauss law, simple. Okay, just related to diverging theorem. Just a simple Gauss law. Okay, just show you the Gauss law, a static law. And here is another application of the Gauss law. Just another application only. And the differential form of Gauss law, that is the divergence theorem. Differential form starting from the divergence theorem, and you can easily rewrite into this form. Divergence E equals rho over epsilon naught. That's the differential form of Gauss law. Okay, that's the first Maxwell equation we use. And divergence B equals 0. We like this one very much because divergence B always equals 0. Always. 洪俊有一个人在大厅外等待哦。洪俊啊 ，OK， 好。Divergence E equals rho over epsilon naught. Okay, and that's another simple mathematics you can calculate by yourself. But I just write it down for you so you can understand easily. But remember, try to derive this equation by yourself. Just plug this part. Try to derive this equation by yourself. Otherwise, you look at this derivation, you say, very easy, no big deal. But if you try to derive this equation by yourself, you will see, oh, not less simple. We should be careful about that. Try to derive by yourself. OK， 动手做了，你才会记得住。Otherwise， 看过都会忘记。OK, that's my suggestions. OK, and Poisson's equation, Laplace equation. E, that's for electrostatic. E equals minus gradient phi. And substitute this one into here. We got Poisson's equation. Okay, and charge free, we got Laplace equation. So no matter you are solving Poisson's equation or charge-free case, Laplace equation, you can always use the green function. The green function helps us to solve not only Laplace equation, but also Poisson's equation. Okay, before that, we cannot solve this one. Remember, how to solve this one? Separation of variable. Okay, for symmetric structure, if the structure is not symmetric, then it will be very, very difficult. Okay, but anyway, for symmetric case, you can use separation of variable, and you can use the special function to solve this equation. And Poisson's equation, we don't know how to solve Poisson's equation. Now, with the green function, we know how to solve the green function, how to solve this one, step by step. Okay. That's a summary of sections 1.5 to 7. Just a simple summary. That's from empirical, from Newton's law. That's Coulomb's force, gravitational force, and Coulomb's equations. And if the test charge is very small, you can write E field as this one. And this one can be for infinite space. You can write into this one. This is a special case. Remember, just consider a test charge Q1, a source charge Q1, and a test charge Q, and infinite space, infinite space. So this is a special case. But luckily, this special case is correct for all the cases. Lucky. Once again, we generalize a special case to a general case. 一个很特殊的 example， 我们把它广义到一个，我们把它广泛的应用到一个更广泛的一个 equation。OK， 这是我们以前用的招式。我只告诉你 special case， 那我就告诉你一般的 case 也是这样子。Show me proof， 没有 proof 哦，只是 empirical equation。那现在可以告诉你我们应该怎么做 ，step by step。OK， derive in this equation. OK, E field, and we know curl of E equals 0, so we can rewrite this part into this equation. Divergence theorem. This surface integral, this volume integral. So it just changed to divergence theorem. And divergence theorem can be write into Gauss law. And you can rewrite into, with this one and this one, you can rewrite into this form. Okay. Different viewpoint, not from empirical, not from special case. Give you a general case. Okay. These are optional because this one is similar to Griffiths. Nothing new, but just give you a chance to refresh your memory. Recall your memory only. So this part are quite simple. And although this part, section 1.6, looks like very new, but from my viewpoint, you will have little applications. Not very useful to me. Therefore, I will skip this part. So you can skip this part if you do not have time. You can skip this part as well as K I. Also, let me try another. Yeah, this one is use mouse. This one is use pad, but I prefer iPad. iPad we can draw directly on the screen. Maybe next time I should use a touch screen. I can write on the screen. That will be much more convenient. But right now, I do not have such a facility. So Okay, that's another example. That for TA, if TA have time, they should talk about this part because we will talk about this part later. Okay, we will talk about the energy, electric field energy later. Okay, so we will come back to this part again. So don't worry too much if TA do not have time. If TA have time, he can tell you how to derive this equation. And the derivation is actually quite simple. You can solve by yourself. You can read by yourself. You should start to help yourself. Self-learning is quite important. Okay, let's just tell you in terms of electrostatic potential and energy, alternative derivation. Okay, just tell you the capacitance. Okay, finally, we come to the homework of chapter 1. We have 10 homework. And the first is related to Green's first, is related to Dirac delta function. And that is another applications to help you solve this equation. Okay, and here are some examples. Calculate the capacitance and solve this one. Okay, simple example. Okay, and so you can solve this one by yourself. TA will solve this one. TA will help you to solve this one. I just talked to TA, both to TA. They will teach you online and record their video and upload to YouTube. So maybe they will separate into 2 parts later on. 现在我们在网络上教，那也许我会做一个网页，把我们的所有的资讯都放在那个网页上面，大家比较好点取，学比较快。Okay. Last one. The end. Okay, that's the end of chapter 1. We still have a lot of time. Any question or comments?
老师，我可以再问一次刚刚那个问题吗？
可以。
就是我们如果看 Jackson 的1.42，
Yes.
应该在蛮前面的。
1.42.
Yeah, 1.42.
Page? Not yet.
I don't quite know. Yeah, the previous one.
Which one?
Previous page, I guess.
1.42. You
That
can
is the
the page. Okay. You do not have lecture note right now.
Yeah, for the moment. Here, this one.
52 or 44.
42. Yeah, previous in the previous page.
That's
Yeah,
44.
this one. 44. But this one is fine also.
Okay.
So say we impose the Dirichlet boundary condition for GD, then
Yes.
we kill the first term for the surface integral. So the remaining part is the same for the one in the slide. But now if we further impose the boundary condition for phi, then the second term in the slide, this slide is also killed. Then the remaining part is just the value integral. So we just killed all the surface contribution.
Not all. We still keep one term. One surface. We still keep this one. This still surface integral.
Right, but I mean, if we further impose the Dirichlet condition for phi also,
Okay,
This
that's
train is also
yeah.
it's also killed.
Yeah, you can do that. You can do that. You can use a grounded sphere or grounded spherical shell. You can do that. Yeah.
That's why I'm a bit confused why we have both Dirichlet condition for phi and GD.
If you, for example, let me show you. Look at my hand. If you have a grounded sphere, this is not a good example. Grounded 文档. Okay, so on the surface it's 0. On the surface it's not sphere. Okay, this way. This is a spherical shell. Spherical shell, right? Okay, spherical shell. And just imagine this is grounded. Okay, in order to satisfy this boundary condition, the green function will be different, not less simple. Because you impose two boundary conditions. One is potential on this sphere is 0. Second, the green function on this sphere is also 0. In that case, the green function is not the one I just showed you. That will be
1 over R.
That will be different. Okay. That will be different, slightly different. This green function will be slightly different, and interestingly, that will be 0 on the surface. Okay, and interestingly, before that, we don't know how to solve this equation, but now, even if you grounded and Dirichlet grounded, you still can solve this one. And the solution is very interesting. OK， 谭道林，我再用中文解释一次哈。Let me reiterate in Chinese. Boundary condition， 你可以把 phi 视为是0，没有问题，因为我用金属把它包起来，难道不可以吗？那我接力不可以吗？当然可以啊，这随你的啊。当然你做实验的时候最好是包起来，就外界都没有影响了。好，这个时候这个是0 ，green function。我们也假设它是0啊，所以这个 green function 有这个边界条件的存在，它就不是那个简单的 green function 了，它会稍微改变一下下，多一项，然后你再把那个 green function 带到这里面来，你这个 distribution 不见得一定要在这个圆的正中央，你可以在任何地方，你都可以算出答案来，所以是非常 powerful 的。以前是都不知道该怎么算的，现在我们可以考虑到这个都可以算。
这个会教吗？还是
没有啊？现在已经可以，下一页就会跟你讲了。下一章 Chapter Two, I will show you how to find the green function which satisfy the boundary conditions. Use special function, Legendre polynomial. Okay. If you're familiar with Legendre polynomial, congratulations. If not, you should spend 12 hours per week. Okay?
Okay, thanks.
洪俊现在有OK. Next one. We still have time. 15 minutes. A lot of time. So just tell you a good news. Looks like our COVID-19, all the infected case per day is single digit. So we can go back to our classroom, room 124, 那个1269级的演讲厅 the first floor of physics building next week, starting from next week. Keep this in mind. 下礼拜上课，我们就正式回归到我们的教室。 有听见吗？因为大家都没有
有
反应，有没有听见？
有
有，
有，
那指挥中心的指引不是80人以上还是不行吗？还是这个
通常我们的同学会 less than 80个
？OK，
，online 会超过80个，但是实体上课应该 less than 80个，通常嘛。那你们自己如果身体有任何的不舒服、发烧、喉咙痛，就不用出席，没关系。好，请在家里面好好休养。但是这不是成为懒惰的借口吼。
如果问题
嘿，请说。
就是如果是回到教室上课的话，那还会录影吗？
这个就是很痛苦的地方，因为一旦录影，那档案都很大。在线上上课录影档案很小，可是在教室上课录影档案很大，然后上传去解析度也不怎么好。那可是我们有旧的一些档案，大家还可以看。物理上应该要梅花座吗？理论上应该要，但是那间教室可以坐到130人，所以大家可以坐松一点点。还是你们比较 prefer 线上上课？大家要不要做一个？我进行一个 survey， 线上好，怎么样？要投票吗？线上上课我又看不到你的脸，我觉得很空虚，你知道吗？看不到你们的脸，看不到你的脸，好像我在对着荧幕讲话，我一直觉得这样很空虚。我比较喜欢 face to face， 看到你的 response， 即使我看到你那种疑惑的 response， 听我讲 green function， 好像讲的跟真的一样，你还是一点搞不清楚，那我至少还可以再讲一遍给你。那现在在线上，我讲 green function 讲完之后，你到底有没有懂，就不知道了。所以老实说，我不太喜欢线上上课，我比较喜欢实体上课 ，face to face， 我觉得会比较有感觉。对啊，当然 face to face 可以距离一点点的，这样比较不会喷口水影响到。好，如果没有问题，我们就暂时下礼拜先回归到教室上课，然后也许要助教录影，教室上课录影的效果通常不太好。讲义会录到，老师会跑来跑去，老师不太喜欢乖乖的待在一个地方，是 movable 的 ，mobility 还蛮大的，所以我会移来移去。那通常会没有抓到焦距，所以我们这个是有改善的空间。所以下礼拜开始，我们先回到教室来上课。哦，那你们考虑一下自己的，洪俊，如果下礼拜我们用录影的，可以吗？
就跟之前一样，应该可以吧？
应该可以嘛，哈。
就是有必要再录一次吗？就是
对啊，有必要再录一次吗？
就是我们其实设备没有说用一个更好的，其实都是用一样的东西。
但是我们应该把它整理得更好，倒是真的，让学生们、同学们比较容易 access，比较不像说现在可能要找第一章要去哪里找，第二章要去哪里找，比较不好找。好，这个我们会尽量改善，会跟助教把这件事情做好，会有一个网页会把这件事情做好。OK。Any other questions？
然后这些 slide 要在哪里找？
slide 都已经放在那个啦，网络上的那个我们的教学网站呢，不是有发 email 给你们，告诉你们我放在哪里吗？
老师，那个 email 好像 Gmail 的部分，有些人会跑到 就是促销信件之类的吧，我听说的啦。
我知道，因为
对，
这个很难避免哦。可是大家要很难避免，但是这个我也没办法叫他不要设成 Gmail，就只有你们自己要把它设成从那边发的，不是垃圾邮件了，这不是我能控制的，所以你自己要去 check 一下。而且事实上，你只要上网站就可以了，你根本就不需要收信啊，你直接去我们的教学网站就可以了。直接去我们的教学网站，那个叫什么？直接去ELearn的系统就可以了。Let me show you。直接去 ELearn system。Okay, for example, let me show you. Let me share this one for you. Just a moment. Let me share. Okay. Okay, for example, you can go to here, ELearn system, your ELearn system, and you can see here, this is electrodynamics, and we have some lecture notes. You can download all the lecture notes here, all the revised lecture notes. Okay, so remember to go to the eLearn system. Our university changed the e-learning system frequently. We have ILMS, we have a EE class, we have an e-learn system. Right now, ILMS is closed, it's canceled, it's obsolete, and EE class is not very convenient. So e-learn looks okay, not good, but acceptable. And I will upload all the file to here, so you can download by yourself. I will announce all the information here, the new information here. So you can download everything here. Okay? And maybe someday we will have a test. For example. Okay. Maybe. I will let you know. And you can upload your homework. If we have homework, you can upload your report for class participation here. Yeah. Okay. So that's for e-learn system. Okay. Any other question? 天福有没有什么 comment？
没有，
你应该都 OK 了，你应该很熟了。你们现在最常用的是哪个系统啊？
就是 eLearn 吧。
可是 eLearn 的系统有点，我不能讲有点蠢，不是很方便，不是非常 friendly。然后寄信还会被人家视为垃圾邮件，真是的。OK， any questions？ 好。邱玉山，邱玉山可以讲话吗？没有麦克风，还是我找一下？看起来应该是喜欢爬山。